trying to think. So this is JSONB time. Just mentioned my name, Peter Gagan. I work through. I like working on fun stuff usually. Sort of, I think marked tendency for me to work on something like that. Although I also like working on things that I want, which is not a bad statement, but I like to chip in where I think that. So as documented, my role on JSONB was a reviewer, and then I had some role in the process of planning a format to make it ready for it. So I'm a bit of a familiar with all this, so bear that in mind. Okay, so what is JSONB? It's simply this information of understanding of large JSONB. So JSONB is quite simple. Is PostgreSQL data. What it's not is a new interchange format. So it's not like MongoDB's JSON. It is purely a new PostgreSQL type, which is to say it will only ever accept as input valid JSON and it will never output valid JSON. And there's of course an earlier JSON data type ever since 9.2, which I think this some comments, but it's important to realize that the JSONB type is distinct from the JSON type. So we're ultimately not exactly, we don't have a like JSON where you have JSON is a binary interchange format, which I thought was kind of an oxymoron. But so this is text in text out, just regard. It's nothing's changed. So these are the two original authors. Oleg Taylor, obviously they can't be here today. Andrew Dunstan played a role with adding functions to manipulate JSON, things like that. He was involved in the whole effort. And on the right, Alexander Korotkov had a role in one of the operator classes, which was discussing. I think is particularly interesting. And still have there as well for Nez Samra Engineering, who played a role in supporting all this work that these guys are doing. Andrew is with PGX, so he, obviously a lot of different people involved in this demo effort. So I want to make that up because I'm only one part of the help effort. Okay, so at a glance, this is more or less directly from the documentation. So JSONB is mostly interesting in that it provides these new operators that are not provided by the original JSON type. These are indexable. So I won't go into detail here. This is essentially simple examples of usage, or we're testing in this instance, for example, containment, as we call it. So we're testing that this is contained here. I'll come to that more later. So this is just discussing some of the rules of containment. I'm not going to go into that just yet, but I'm not going to go into the slide. This example that illustrates the compelling case for containment. So you have this. This comes from a set that we used for development. It's just a set which is bookmarks, and there's a sort of an implicit schema where we have all this nesting going on here. These tags where we have an array containing an object, and then we have a term, a label, scheme. So anyway, this example illustrates how we're sort of reaching in, if you will, to the JSONB in the query predicate. So the containment is such that we can reach in, if you like. So we're not touching any of this label stuff, nor are we touching this scheme stuff. It's perfectly sufficient that we're just specifying the terms. And we have to specify the nesting level. So we're, we have to put in tags at that level there, which match up the array containing objects. That's it. So this is, quite a flexible approach. Of course, the schema is from a third party, so they haven't particularly optimized it for Postgres or any particular system, and yet this performs very well. Let's see. So anyway, taking a step back, why would we have both JSON and JSONB types? Isn't there some kind of redundancy there? Perhaps a little, but in main, I would suggest that the fact that we have both is not just a historical state. In fact, there are use cases for both, although I would also suggest the JSONB type is in general the more compelling to it, and you're probably going to use that, unless you are aware of a specific reason not to. So, JSONB is a binary type, as opposed to JSON, which is a text type. The internal representation is entirely textual, and so white space and like that will be preserved. Character and so on will be preserved in JSON, where in JSONB it will not. There's also a deduplication process whereby pairs is contained within the object container type, which is hash container type associative container. Those are deduplicated on input. We have a last wins policy. Furthermore, the order of these pairs within a given object is defined by the implementation. We pick a convenient ordering to facilitate cheap binary searches. So, for this reason, there's the CPU overhead of parsing, or performing any of these various operations on JSONB is very low. So we use this convenient, arbitrary ordering for the purposes of searching through this, an object. So it's something to be aware of, because if you are relying on the object pairs being in a fixed order, you're going to be disappointed. But in fact, you're probably not relying on that. It's probably reasonable to suppose that you don't care about that in general. So yeah, I mean, it's this sort of simple fixed ordering. This is something that the RFC, the recently ratified RFC, explicitly anticipates it allows for. So we think that's right trade-off.
A couple questions. Yes. One, when you say deduplicates pairs, you mean you can have duplicate keys but not duplicate pairs, or?
No, I mean that if you have duplicate keys in a key value pair, those will be deduplicated entirely by virtue of having duplicate keys. The values themselves do not matter.
That's a pretty opaque data.
I didn't quite follow. So if you have, key A and value 1 and key A and value 2.
Yes.
Is that okay, or will those be deduplicated?
It's okay if you don't mind being duplicated.
So you lose A equals 1, is it?
Yeah.
Standard map semantics.
Yes, standard map semantics, not multi-map semantics or any other. So that's something that the standard anticipates. Doesn't require a bid. We do it because we find it to be convenient for other reasons. Okay.
Which RFC is the JSON?
The recent JSON RFC, I don't recall the exact RFC number, but the document in that case.
And then, so would you say JSONB is the one that follows the RFC, and JSON?
Well, they both follow the RFC.
The RFC leaves these things, especially RFCs, concerns all these things are implementation dependent.
It's like a C standard.
Yeah, they basically they rather than force some level of conformity, they basically took all of these implementations and simply made a Chinese menu out of it.
So I think they say, here's what you might want to do, and we basically do some of the things they suggest about it. This is some of them I'm calling out specifically. So you might reasonably say, my use case doesn't allow for that, and therefore I can't use JSONB. But in my estimation, at least, I think you probably won't say that. I think you'll probably say, this is okay, I'm okay with this, and I'm willing to, or, it's in type or Word or whatever.
Any kind of like a C data type thing where you can't keep white space, or are you back to JSON data typing?
You're back to the JSON data type if you want that. The white space is semantically significant, so it's going to be, when you serialize on input, it's going to be dissolved. So that's going to be preserved. Sorry, Tom.
I was just going to say, if you have a situation where you need that most of the time, you could conceivably store the data as JSON when you want to operate on landscape operators. Force JSON, you don't fly. Yeah, it's true. It'll cost you some performance, but you can do it.
Good point.
Okay. That is a fair point. Shall we move on?
Okay, just one other question.
Yes.
Some way of doing it that I'd like to actually error if there's duplicate keys. I could imagine. Is there any way to use them?
Another option immediately occurs to me. I didn't consider the question. Perhaps I should consider it in more detail. I'd have to think about it. But I think it is mostly non-issue, to be honest.
Sorry, what's the shadow type?
Well, a shadow type is a term type event, which refers to the typing that exists within the JSON data type, which is to say, it's something that the SQL parser does not have direct knowledge of. Rather, the implementation is in effect defined in terms of for Postgres types. So that's all that's going to occur within the input parser. For various, it doesn't necessarily come up that often with the initial implementation, but for various purposes, for example, sorting, the sort order is defined in terms of, say, the numeric sort order or the text sort order. So that's one of the shadow types. It's really just there's no abstract concept of a shadow type. I'm just using it as a sort of an artistic way of referring to that concept. If that makes sense. Okay. So that's what I'm referring to here. So that implies that because one is defined in terms of the other. For example, for arbitrary precision, in contrast with many implementations that, again, as you see before by the RFC, use IEEE floating point representations. We do not. We use the numeric representation. Exactly as you would expect, you can store, trailing zeros, and they will be preserved without being semantically significant, which I think is a nice touch. And you'll have sort order. So usually you don't care about the sort order of JSON, but if you're like subscripting JSONB or by, what is currently a string primitive type, that's going to sort using the default collation. So that's probably when you care about it, when you do stuff like that, or even you could be reaching in and extracting a number equally well. So we do support this sort of raw scalar, as you see here. So that might be extracting a raw string. Okay. So there's this parallel set of facilities. It's a much faster in typical cases. It has indexable operator class, but we'll discuss what they are in a little while. In contrast to JSON, this makes very effective GIN indexing possible. So as I said, in my view, most people are going to want to use JSONB. So there are one or two edge cases to be aware of, though. And I'm going to talk about those. And also, this work completes without really going into them. These are various functions that will allow you to, unnest JSON, potentially manipulate it using SQL. That kind of stuff exists a lot. I'm not talking about much today. I'm going to talk about indexing in more detail. Quick aside, this is actually a visualization of the Postgres B tree, not a gin. So, but if you actually look at the original, it's ridiculously wide. You get it on 3 layers, 3 levels. And I'm kind of pointing out that there seems to be a misconception people have that a B tree is like a binary search tree where it's very tall structure, but in fact it's ridiculously wide structure. So I just want to mention that in passing because there's this widespread misconception that they look like.
Well, if you have 10 billion values, it can get tall.
And
Well,
Very tall.
no.
Depends on how wide that is. So.
Well, yes, but in typical cases, it will not in fact get very tall. So anyway, what are operator classes? So they describe a contract between the data type and the system for indexing. We do have the basically default B tree and hash opt class. These are not that interesting for the purposes of indexing, but because these various AMs have hard-coded significance system dependencies on these AMs, you might say the B tree operator class in general represents how we want to sort.
What's the name?
Access method. So an access method is a general scheme for indexing. So I've already mentioned gin and B tree will be examples of an AM. So the B tree up class is mostly about how we sort as opposed to indexing B, because indexing JSONB is probably not something you're going to want to do that often. So this is mostly discussing caching for various operations rather than building hash indexes. So it's mostly of interest for I mentioned hashing for completeness, but the B tree class, how we determine how we sort JSON is interesting. But I already mentioned that. So that's really just how it's implemented as an operator class. Although it's also what it possible if you were trying to create B tree index on JSONB column. Okay. So I think I've said enough on that. So I'm going to go into the generator classes in detail. Okay, so this is JSONB path ops, and the default one, well, both use hashing internally, but the JSONB path ops much more so. The JSONB path ops op class tends to produce indexes that are very small in size. We'll see figures for that soon. However, it doesn't support an existence operator, so it is somewhat less flexible. And we'll look at that in a moment. So we have this. These are the various operators as documented. So I've already talked a lot about containment, where you're reaching in. This is the existence operator, which at the top level determines if that key exists in the JSONB. So this would yield true. But it's only at the top level. These are just various. Just any of these exist, all these exist, which are, they're self-explanatory, I think, based on what I've already told you. So these are the things like B tree. But for the GinOp classes, these are the indexable operators. Although, as I mentioned, JSONB path ops only makes these containment operators indexable. So maybe the existence operator is something you consider to be compelling. But I would suggest it's not looking that. Here's what I think when you should use one or the other. So the JSONB path ops class uses that work best with when you're doing a lot of containment. I consider containment to be the compelling thing to do with JSONB. So the default we use for existence is more for your classic H-store use case, where presumably there's a lot of patterns that key byte pairs. That might, so you would reasonably want to test existence all the time. In general, as with the document databases, more often than not, there'll be a somewhat fixed structure, be it enforced or unenforced, and so testing whether or not keys exist doesn't have that compelling. So I would suggest that to look to the JSONB path ops. This containment will get you an awful lot for that use case. There'll be additional benefits, performance benefits to doing that at what I would consider to be usually acceptable costs and flexibility. I have a caveat here about queries that don't contain GIN keys. I'm going to go into that in more detail in a little while. Also, noting that expression index can be used, and probably will be used extensively with JSONB. That's this concept that when you're declaring an index, it be on the expression, typically it's JSONB, you're subscripting the JSONB, so it's an array that is expected to be in every single JSONB that is inserted. So you could potentially subscript that within your query, and then consequently your index would be a lot smaller because you're not indexing things that you need to index. So it's not, yes?
I just have a really simple overview question.
Sure, sure.
The JSONB path ops is it's an index modifier. It's a way in the syntax when you declare the index to say it's going to use this flavor or this path.
That's exactly right. The semantics of containment are minimal. It doesn't matter what. It's still going to give you the same result, no matter what up class you use. And those work for containment. But there are other advantages I'll go into shortly to limiting yourself to using the JSONB path ops up class. There's good reasons pertaining to performance why you might want to do that at a small cost and flexibility. But either way, contain operator always does that one thing. The existence operator always does that one thing. It's just that, as I said, the paths that's only going to store.
When you find the index to say using GIN, JSONB column, right? Path ops either yes there or not.
Right. You have to specify. There's a default, which is the JSONB ops, which is the one that says more flexible, and there might be fewer caveats about. But in general, I think you ought to certainly consider using JSONB path ops because in many cases it's far more compelling.
Well, that's a fine point. I'm interested to hear what you say about it.
Well, okay. So what is GIN anyway, in general, in the abstract? So it's an extensible infrastructure. So occasionally described as a tree of B trees. So it's basically an index type that's optimized for cases like text search, or for searching through arrays in a table where you might want to search for a particular element or elements. You want to see any rows that within their arrays contain those elements, things like that. So it's optimized for the case where there's a lot of duplicates, which is not something that's handled so by the normal B tree code, for example. So all kinds of optimizations around are duplicates. So I think the stated main goal of it is to power text search. So it always contains these keys. They're stored in the format side by the op class. It's not something that the B tree type proper allows for.
I think there's another worth mentioning, which is that GIN is capable of storing multiple keys for the same indexed value, which classic B tree does not do at all.
Yes.
So, for example, if we have a array containing values 1, 2, 7, each 1, 2, and 7 can each be stored as separate entries in the index, and you can look for those, and then go back and find rows containing that as one of the elements of their array. Whereas with this classic B tree, you could only store the entire value of 1, 2, 7 in some way, and search for that whole thing.
Right. So your op class, an extensible infrastructure. So the op class author is making sort of coming up with a contract between Gin and the data type. So with B-tree proper, you're not obligated to store it in any particular way, whereas B-tree requires that, whether it's stored in the index, as the original type. Matter of deciding what the storage type is for the op class, and I'll go into that as it pertains to JSONB just now. So JSONB path ops, the hashing op class, if you like, stores only 32-bit integers, hash values. The default op class stores text. And to the number of gene keys, which is a concept that has nothing in particular to do with JSONB, it's going to vary. The different strategies of each op class, which I think we're going into more. So the JSONB path ops will store a hash of a nested primitive JSON value. Any keys that are taken away as you're walking through representation, going through objects, you're going to go through keys. Those values are going to be mixed into the hash, making them more exact than they might otherwise be. Whereas the default text op class will generally store a full text copy of each JSON key and values separately. Even number parameters as text. So this is the on-disk representation in both cases is entirely distinct from JSONB proper. So to make that perhaps more concrete, I'm just illustrating here how each op class. So this is an interesting case here because when it's empty, thus there's no empty JSONB path ops gin key. Actually, I think I've inverted this. I'm sorry. So what I'm trying to illustrate here is that these values are ultimately one gin integer, which is a hash, which is a function of not only the value itself, but keys that you would put on way in getting to the value if you like. In contrast, the JSONB ops will store a lot of redundant information about there'll be a gin key, if you like, for every one of these, as opposed to at the deepest level. Now, gin is good at handling a lot of duplicates, as I mentioned. That's not that bad, but we can work within the limitations of the JSONB path ops. We've got to try. Now, if you were to query this source empty with JSONB path ops, that would have full index scan, which is bad because there's going to be no JSONB path ops hash value to look for, so you avoid that kind of thing. But then you probably weren't going to do that anyway. That's something to be aware of. There are one or two hazards like this that you must consider. So what does Gin know about JSONB? Only knows what the op class tells it. Fundamentally, Gin only knows here are some keys, and where it points to in the table. There's no direct representation of the nested level. So it has only an idea of the underlying JSONB. So when we're querying, there's this process through which JSONB is broken up into storage representation for querying index. A similar process occurs when inserting into the index initially. So in and of itself, the index is only reliable for telling us where values cannot be. So we need to recheck to make sure. I mean, most obviously, there could be hash collision, but there are problems as well. So it's necessary to recheck for that reason. However, this is not inherent to Gin op classes in general. It's just something peculiar to this these particular Gin op classes. So a little on the structure here. Only returns rows that match that I mentioned. Now the next can must be check. That's not an inherent property of Gin. So that's just exactly what I just said. So which should I use? As I mentioned before, just path ops seems like the way to go for the most common use cases. If you can bear these one or two things in mind, you can reach in at multiple points. And there is existence, as I mentioned, more of the classic short use case. You know, any particular structure, JSONB datums within your table. That's perhaps the case where existence is more compelling, and thus you don't want to give that up.
Let me see which multiple points.
Well, if you go back to your containment example, I have an awful lot of leeway in terms of what I'm putting in that predicate, because if you look at the actual document, I put tags and then term. There's more than that in the actual object here, right? The term .html and it's got a bunch of other stuff that I don't care about. So I'm reaching in the sense that every single term I'm reaching in there. I don't quite specify anything else other than you know. Okay. So what's it fast? What's JSONB fast? Well, it's very selective. Only your nested values are stored as gin keys in the first place. You've less to store initially, obviously. Unless it's later. We're only using G in comparison because storage is just a 32-bit integer type, and thus, you know, it's really cheap to do it. It's an integral operation to do it for comparison. So this JSONB path ops thing is lightning fast, as we'll see. And the length is relevant. So you're just, because a hash value obviously doesn't matter if you have, you know, in terms of loading index, it doesn't matter how long your keys or values are. There's actually a fallback for the default password, but it will occasionally hash as well. But it's something that it tries to avoid when it can. So we're trying to anticipate future uses of the class because we've effectively committed to that representation. So we want to try and make it as general as possible. Okay. I mentioned again the edge case that I already highlighted. There ought to be some object value or array element in the JSONB image predicate, otherwise you'd have this problem. I also should mention that gin is generally better than 4, an awful lot of work when it is, which is technically totally incidental to all this, but it just so happens that the original rationale was for speeding up full text search, but we sort of have these, I guess you could call them synergies, if you forgive me, where, you know, so the sort of tagline this, not tagline, the sort of, you know, the single quote that encapsulated this was, oh, it's going to make full text search from Postgres faster than a lot of external systems, and it appears that that's the case. So it's sped up, but incidentally also made JSONB a lot faster than it would have been, which is pretty nice. So we have, I'm not going to go into this in too much detail. Index is a lot smaller, and we have keep skipping optimization, and we have this rare and frequent optimization, likely particularly beneficial for the default op class, where there might be a lot of the same key. Okay, so I'm going to go into a little bit on, you know, give you some actual numbers. Again, talking about the delicious sample data set. So this is a bookmark data widely available. It's on the internet if you care to look for it. Bulk loaded into PostgreSQL using copy. And the default, sorry, the size when stored JSONB is approximately 1.3 gigabytes. A JSONB ops index on that data is 636 megabytes. That's the figure with no compression enabled. JSONB path ops 295. So these are considerably smaller than the proper, which reflects, you know, certainly that the compression within gin is effective, but also when you're hashing, you know, that's almost unbeatable in terms of the actual on size of the resultant indexes. I mean, by the way, these are indexes over the entire structure we've already seen, which is quite a complicated structure. So, you know, the fact that they're so much smaller, I think, is backed on the implementation. This is a example of a expressional index only on tags, which again is much smaller. You might limit yourself to missing just the tags, and you can get it down to 4 megabytes approximately in that way. So even when we're totally discounting the need to consider what you actually query, that's, you know, you're getting a 295 megabyte index on a 1.3 gig, which is pretty nice. Yes.
Great. So I guess when I think of storing a hash, I think of starting a version. So is that the actual text representation gets stored anywhere alongside, or is there?
Well, it's stored in the table itself.
I see.
But it's sufficient to just hash it within the index, or hash in the index while rechecking to make sure that you didn't get a collision or whatever. I mean, even if you did have the full copy of it, it wouldn't be sufficient because the opposite node that structure confused for other reasons. But essentially, it's sufficient to only store a hash provided we can recheck, which we can when we visit the heap table.
So there's a lot of redundant things. This is part of just moving from the pod is that you have to.
Well, it's sufficient to find the data, and that's all we need.
Okay.
Yes.
You're saying the table that stores the data, these are the sizes of the indexes that were built in addition to the table.
That's correct. So the main table is 1.3 gigabytes, and these are indexed on that data. In this case, indiscriminately on every single item in every single row. Being more selective, we get it to 44 megabytes just for the tags which we're talking.
I'm wondering if you have an idea of how much of the data is tagged as you extract just the tags you'll store the JSON.
That's an excellent question, and the answer is no, I don't know.
Okay.
I can only presume that it's considerable of the total because anyway, it's more or less designed to query, so it'll typically be 3 or 4 or 5 of those per entry. So I'm trying to, but it's I think it's probably representative of the fact you can get it down quite small.
If you update your presentation and consider that, you might also find a little information on numbers of rows. So,
I can give you some numbers on that if you.
Okay. Well, only mildly curious. I mean,
Sure,
it's only relevant in context to the specific.
It's an interesting example because that motivated some of the design decisions we made. Obviously, we did consider what other people do a little. We took a certain amount of insight what other people do. I'll continue. So the storage overhead here, as compared to JSON, is pretty modest. We have some overhead as compared to the original data because we're using page storage. That does imply some overhead as well, but it is, fairly modest. There are cases where JSONB comes out ahead of JSON, depending on things like the size of the data as it relates to the overall complexity of the structure, because there's additional storage overhead for some metadata. On the other hand, you're not storing as much stuff like white space. So it can come away. In this instance, we're a little bit behind in terms of we lose a little on things like alignment. So there's a modest additional overhead on pretty on at the table level. The indexes. Well, I mean, there's no basis of comparison because it's for JSON, but even though the indexes are compressed a lot better. So anyway, sequential scan over this is the total number of rows removed, so you can and this is the total number of rows returned, 285. So for 1.3 gigabytes, that's a little over a second there. That's not too surprising given this is well cached data in this example.
Quite good.
It's very good. Sequential scan, it's pretty good.
JSON type much slower.
Right. Now, I should also point out we're turning 285 rows here, and those 285 rows need to recheck each and every one of them as they're returned. So that implies an additional overhead. It's not a highly selective query. Now I'm going to show you how it performs with each of the indexes for each of the GDOC classes. If there are relevant indexes available, how that will perform.
Can you explain why you have to recheck the rows?
Right. Well, because the information actually stored in the index is, in this instance, in the case of this particular GNOP class, not sufficient to be absolutely sure that whatever it is to really does, really is what we're looking for. It's only sufficient to determine that, here's where any of them that might exist are, if indeed there are any. In practice, it's probably, I think in this instance, there's nothing limited by the recheck. So, I mean, with hash values, you could have, for example, a hash collision. And also, we don't know the structure of the JSONB within the index, and the semantics that we implement may imply that that matters. So we could make mistakes if we were to rely entirely on the index. But this is something that's peculiar to JSONB. It doesn't apply in other cases where GNOP classes are used. So it's not an inherent limitation of GIN. It's just a limitation of the word. Anyway, moving on. So looking at the default op class performance here, it's quite a lot lower, 8.5 milliseconds. So it's being indexed effectively. Again, not very selective. I mean, it's selective, but it's not. It's only returning. It's returning 285 rows. So there's an inherent overhead there. This is the text storage op class. Moving on. This is the one that's really compelling. So with the hash-based op class, JSONB path ops, got it down to 0.6 milliseconds, which is pretty nice.
But it's actually showing there were no false matches in this particular search.
Right. Well, that's surprising. But once again, this is 285 matches. And so if I go back to my original example, way back when I was looking at something that would only return one row in practice, which is, I think, this one. I actually ran this query today, and on PostgreSQL with debugging symbols, with descriptions enabled, and because it only was taking one row out of the table, it was like a fraction of 1/10 of a millisecond or something like that. Vastly, faster than the example given a relatively large number of rows turned. So for stuff like that, it's just lightning fast. It's incredibly well performing. So that's why I would consider if basically path ops is suitable for use case, because it probably is. You're getting very, very good performance for that. Okay. What else? Okay, so this is just a reflection on what I think of JSONB in terms of its strategic significance. This is my blog that I link there. So I think it's going to make Postgres competitive with some of the document EPs. On the one hand, I think it's not really that much of a change. It's not a fundamental change of direction for Postgres, but it's entirely natural that we would have something like JSONB. If you look at the history, certainly we've had HStore since 2006, with MAC address type, with an XML type, and so on. And Postgres is just a set of data types, essentially. So I really don't think that this can be, on the one hand, I think it can be interpreted as so much a response to others, as why don't we have this? We're perfectly capable of supporting it. People seem to like it, and yet, I think it is going to be very competitive with some of the other systems. So that's really my take on it. Others may have different views. This is a major goal for Postgres all along. It's people got very excited about JSONB. A lot of people on the internet at large got very excited about the JSONB type, and a lot of the core developers are what all the fuss was about. I think both are right. Yes?
What is a selectivity estimator?
It's a way of determining how selective a predicate is for the purpose of usually where you're determining whether or not you use an index.
Okay.
So this is something that PostgreSQL makes particularly useful. I think Post kind of in the original reason for making it acceptable. I'm not sure of this. Anyway, so I'll discuss futures here. Ultimately, it's not really in my bag, but you know, I'm sort of I'll comment on this stuff because it seems to be stuff other people are interested in. So I'll comment. I'll tell you what I know. So this vodka AM that's been proposed at PCon back in May. So this is somewhat like gin, but it's using a suffix tree, which has all kinds of prefix compression. So I'm not really sure what that is, but it's something to do with having suffix trees, but binary trees for numerics. So it knows something about the types. It's quite going to be used for compression that preserves the full representation of the datums within the index, things like that. That's very much up in the air. So you know as much as I do at this point about that. This JS query language, which is sort of Java that they proposed, where you have like this sort of special subscripting syntax. Wouldn't be part of the SQL parser or the shadow parser. It would do some of this. Excuse me. So that would allow you to sort of subscript it in a way that I think is similar to MongoDB. I think there's also use cases around partial matches to strings. Everything I've shown you assumes that whatever you're looking for, you can provide, you know, an exact match for, in the case of strings anyway. You know, so I think this has something to do with partial matching of strings. So this is very much research. There's nothing I can say about it, but I pointed out as being an interesting area of future development. Statistics, sleep for characterizing the distribution of data within JSONB. That's something, and there's another project that there's some interest in. I'm not really very sure that it works. So let's say on that. I'm just noting it for to be complete. Pretty printing of JSONB. This just didn't make the cut for 9.4. There's no reason we ought not to have a pretty printing facility, so you can easily visualize JSON or JSONB. That could be a useful thing. Of course, you're not going to see whatever representation you might have initially used. That's lost. But you might see, you know, making it more easier to read. That'd be a useful thing. We also lost a concatenate operator. Concatenate JSONB is what you can store just like put. No good reason why we couldn't have that in a future version. I talk a little bit here about this idea of doing some talk as well around delta-based row versioning, whereby you would update and then you'd only store information sufficient to recreate the original row, you know, in a differential fashion. So you would, you know, you wouldn't be storing as much. I'm not sure that's actually as compelling as it sounds. I don't know that it's going to be worth the considerable difficulty of coming up with an extensive infrastructure to do that, but it's something that people express interest in anyway.
How would you ever vacuum?
Well, exactly.
And storage is free anyway.
Yeah, I can't. I'm not going to tell you. I know Mongo with Couch. This was actually an issue because they actually did store deltas. It would never remove anything.
Really?
Yeah.
Yeah. I mean, I can imagine that. You know, it's counterintuitive, but I imagine that it's actually kind of hard to justify the effort you would have to go to make something like that work. It's not obvious. Yes.
So what's going to happen with HSO1?
Well, HStore, as I mentioned, this is basically a derivative of HStore, although obviously we've added quite a little bit more. I perhaps that HStore is going to be, a way of simple key value representation where you must be your indexing text. I don't think we're going to work more on HStore, but there's no plans to deprecate it or anything like that. There are some casts available. You can cast HStore to JSON or JSONB. So potentially you could do it. You could do a migration sort of piece of fashion using that approach. But it's not something I would anticipate we're going to do too much more on. But at the same time, there are no plans to deprecate it or anything like that. There's no reason why you can be able to continue to use it if you want to. Does that answer your question? Yes.
So if you just want to store simple key value pairs in the database, do you guys always go with JSON, or is there any advantage to it?
I see no advantage whatsoever, except perhaps the availability of something like a concatenate operator. The indexing strategies just between the two are very similar. I would be very surprised if there's any major advantage to using HStore at this point, other than it's what you built your app with. There's no reason to worry about it if you have a reason to, you can store and receive feature. Do I have any? Okay, I think I'm done. Does anyone have any questions? Any further questions?
This is important.
That's right. Yes.
And the HStore is not.
That's all. Yes, that's correct.
And actually, one of the things that we've noticed is that a chronic problem in Postgres development is that we don't currently have any way to move types in or out of order.
Right.
That is, if they're an extension type, they're an extension type forever, and if they're a core type, they're a core type forever.
Yeah.
Which is kind of a long development program for it.
Right.
So full text search. Full text search.
Yeah. I think the only reason we're able to do that was because prior to putting it in the core was pretty buggy anyway. It'd be a lot less used like it.
But you don't read manual about the migration process.
Part of the
Yeah.
actually one of the changes is
Yeah, that's it. But we didn't actually get PG upgrade at the time, which.
Yeah.
A bit more about your index, how you select what things go into the index or not. You should if you pick one case, everything.
That's an expression index. Just in particular to be just that I suspect many people will find that unuseful to use expression indexes with JSONB. So you're indexing, but you're still particularly JSONB and effectively creating new JSONB with all you index, as opposed to indexing everything.